P2 V2 over P1 V1.
Okay. So to solve for T2, I mean, everyone thinks about algebra kind of differently. So like, how do you think that through?
I cross-multiplied and then I divided by P1 V1.
Okay, so since you only have one term on each side, you can totally cross-multiply, which is totally not the way I think of it. So that's great. So if you cross-multiply, that means you take the numerator on one side and the denominator on the other side and put them all on one side. And then you do the same. So numerator on that side, denominator on that side. And then you just pick the one you want to solve for and solve for it. So P2, V2, T1. And then you just divide through by these two. And you're good. So the way I think of this is, if it's in the denominator here, I just move it over to the numerator there. And then everything that's denominator on this side will be numerator on that side. Everything that's numerator on this side will be denominator on that side. And of course, I'm not messing with this side. So P2, V2. And then T1's going to be numerator because it's the opposite. And then these guys are going to be denominator because they're the opposite. So I guess it's essentially cross-multiplying. It's just not what I'm thinking about.
Yeah.
I just wait for the math people to solve it, and then I memorize the new paper.
Okay, must learn to solve it, because
Nice.
you never know what you're going to have, on the test. Perhaps he's going to, make you solve for V1 or something. So just make sure you can manipulate this equation, or, it's going to end badly. So please leave your book right there. So practice problem 1. Maybe we're on Liam. A balloon is filled with hydrogen at a temperature of 20 degrees Celsius and a pressure of 755 millimeters of mercury. So when you are doing these problems, I highly recommend that you just write down all your information. So what did that just give us? P1 and what?
Temperature.
Sure.
And T1. So what was P1?
755 millimeters of mercury.
Is it 3 significant figures?
Yes.
Okay. And T1?
20 degrees Celsius.
20.0?
Yeah, 20.
What?
Yes.
Oh! I think I got it wrong. Okay. Oh. Well, that's really bad.
The temperature, it says temperature stays the same.
Yeah.
So you
Oh,
don't need
good.
to
Okay,
use
I
that.
didn't get it wrong. Okay. So if temperature stays the same, I don't have to convert it to Kelvin or worry about it. I'm thinking significant figure nightmare, because that would be one significant figure in the tens place. That would make your problem, that's invalid. Just get new data with more significant figures. If the balloon's original volume was 1.05 liters, what will the new volume be when pressure changes? So V1 is 1.05 liters. And what is the new pressure, Liam?
625, sorry.
Millimeters of mercury?
Yes.
Okay. So, we just need to know V2. So, what equation would we use?
V2 equals P1 times V1 over V2.
Okay. And what is that really? Boyle's Charles, unnamed, combined.
Boils.
This is Boyle's law. Constant temperature, P1 V1 equals P2 V2 is Boyle's law. So then we just plug in, and what do you get? What I plug in. And what do we get?
I got 1.27 liters.
So does that make sense? Would volume increase when pressure decreases? Tell me what you got again.
1.27.
I think that sounds right. Because think about it, right? Pressure has decreased. So like say you have a balloon. If pressure outside it decreases, what will happen to the volume of it?
Sorry, say it again.
Okay, here's a balloon, right? It goes up, pressure up high is decreasing, but the gas inside the balloon is exerting the same amount of
So
pressure
it'll
out.
expand.
So it'll expand. So when you think through at the end of a problem, right, pressure has decreased, you think, well, there's an inverse relationship between pressure and volume. So if pressure decreases, volume should increase. If you don't see that happening, maybe you've made a math mistake. And that is probably what I got. Yep, 1.27 liters, 3 significant figures, so that's all good. But always think it through just in case you've, written the equation wrong or made a little mistake. This is the biggest module of little mistakes for some reason. I don't know why. It just seems to be maybe the time of year when people are stressed. Okay, so Jolene, a bacterial culture isolated from sewage produced 46.1 milliliters of methane gas at 25 degrees Celsius and 780 torr. What would the volume be at STP? Okay, so let's just set up. I wish I had more markers to work. Is that pack of markers still on my bookshelf that someone gave me for Christmas? Yay! Okay. So I'm going to stop writing in pink that the camera can't see. All right, so Jolene, what does the problem tell us?
I thought we were finishing off module 11.
Okay.
So I don't have any.
That's fine. I think this week is kind of the week of nobody is quite prepared, but that's okay. So can I borrow your book and let Jolene read out of it? All right. So let's have a look. We'll talk each other through it. So we've got this bacterial culture, and it produced 46.1 milliliters of methane gas. So what would that be?
Pressure.
No.
That's volume.
46.1?
Yeah. No.
Okay. And what else did it say? Keep reading.
Of methane gas at 25 degrees Celsius.
Okay, so T1 would be 25. Is it 0.0?
No.
Just 25.
And 780 torr.
Marker writing.
What would the volume of the methane be at STP?
Okay, so what will STP tell us about these three things? So, standard temperature, Jenny, that was your question. What's standard temperature? You guys need to memorize standard temperature and pressure.
No, standard temperature is the next one.
I'm just asking you what literally is standard temperature
Oh,
in Kelvin.
in Kelvin?
Yeah.
273.
And what is standard pressure?
That's in the other one.
Standard pressure.
Is it 760.0?
Right. So when you memorize it, you're probably going to memorize that standard pressure is 1 atmosphere, but we know that's 760 torr. So when it tells you a problem ends up at STP or starts at STP, that's giving you pressure and temperature, even though they're not directly stating it. So you have to memorize those. Okay, so now let's think about our units, Jolene. We've got pressure and torr, that's good. Milliliters is fine for volume, but yeah, so all gas laws have to be in what? Kelvin. So how do we convert to Kelvin?
Plus 25 plus 2, 37 plus 15.
And so when you do this, if this is significant to the ones place, you can only keep to the ones place. So you're only going to keep 3 significant figures. So what would it be?
I got that.
the touchy little details of
You have to go way back to
significant
module
figures.
1.
98.
Crazy.
You actually didn't find the answer.
298 Kelvin.
Like the answer is right.
I think 298 Kelvin is actually standard condition, which you guys will learn about later. And then he'll give you problems like, it starts at standard temperature and pressure and ends up at standard conditions. Oh. So, now we have everything we need. What equation should we use?
Just combined gas.
Combined gas law. Alright, so, how do you like to do it? Do you just plug it in or do you solve for V2 first? Plug everything in. That's kind of what I do. Alright, so I'll start plugging in while you start calculator in. Do you have a calculator? Do I have a calculator? I don't think I have a calculator. No one is prepared for that. This is like...
I have an extra one.
Oh, I'll steal Jenny's because it's the right kind for me. 298 Kelvin. What am I doing?
No idea.
I can see how it's easy to make little mistakes. But show your work, you get partial credit even if you make a little mistake if you've shown your work. There's our variables, or unknown, I guess it's not varying. Okay, so if we solve V2 here, eventually, what will we get? If you haven't done it, feel free to do it. Oh, and while we're doing it, I will dig up the tiny lab apparatus, which is probably lost deep in here. Oh, no. It's how we demonstrate Boyle's law, except it's not. I had it and then I messed it up. You just have to like make the water grab because of cohesive forces in the water. Alright, we have some definite error going on. Maybe dropping it will actually help too. I'm not sure.
It's right there.
Oh, thanks. I don't want to step on it. Boyle's law can only go so far when you have a plastic syringe, and eventually pressure will be too great for the apparatus. Crooked table. This is fun. Okay. Okay, I can't wobble too much now. Okay. So, do we have an answer for V2?
Is the P1, that's just two significant figures, right?
P1, is it,
So there's no decimal.
This is 2.
it's 2, P1 is 2.
So there'll only be two.
Ooh. Yeah, it is, it's really 2. So, think it through. Pressure has gone down, temperature has gone down. So what will happen to volume? When pressure goes down, what happens to volume?
Goes up.
It goes up. When temperature goes down, what happens to volume?
It goes up.
So think of a bubble. Like, have you ever had a soap bubble form on top of your shampoo in the shower? Yeah. And then what happens as the shower gets hotter? Right? It expands. So volume goes up as temperature goes up. So as temperature goes down, volume is going to go. Well, temperature is going down, right? From yeah, 298 to 273. So for this bubble in the shower, it's going to expand because temperature is going up, volume will go up. For this, temperature is going down, so volume will down. So pressure going down will cause it to expand. Temperature going down will cause it to contract. So what do we expect? Probably pretty similar, right? One thing is making it expand and one thing is making it contract. So I doubt volume is going to change a whole lot. So we should really expect something fairly close to 46.1 milliliters. So if you get something vastly different, maybe a mistake. Do we have an answer? Anyone?
I got 43.
Yeah,
43. And you can only keep 2, as Lily pointed out, because this is 2. So 43 milliliters, not vastly different than 46 milliliters, so that's good. But if the plugging in and actually solving on a calculator is a challenge, practice a lot. Do the problems over and over until you're really comfortable using these equations, because people get tripped up in this module a lot with the algebra. And if you show your work, it'll go well even if you plug in kind of wrong, but you'll miss part credit, but not terribly. Is that the last? We have one more? One more. All right, back to Brittany.
I didn't do this one.
Oh, that's okay. That might be the best way to go today. So we've got a steel container with a volume that can't change. And it's filled with 123 atmospheres of compressed air at 20 degrees Celsius. Ooh, if it sits out in the sun all day, its temperature goes up to 55 Celsius. So what's the new pressure? So if volume doesn't change and temperature goes up, what do you expect to happen to pressure?
It goes up.
Yep. When you get a gas hotter, it tends to want to expand. In this case, it can't expand because it's in a constant volume steel container. So it's going to just increase in pressure because it can't expand. I'm in the color. Okay, so what law relates pressure and temperature to constant volume? Is that the
What is it Boyle's law?
Boyle's law is PV is constant at a constant temperature. Charles' law is
Pressure is constant.
what's the thing?
V/T.
That's Charles' law. But this is pressure and temperature, right? So when we look at the combined gas law, we're going to see, right, if volume's constant, we're still going to have this direct relationship. So maybe I should make that a 2. All right. So let's plug in. What do we see?
Okay, so the steel container has a volume that cannot change. It's filled with 123 ATMs.
Is it 0.0?
Yeah, 123.0. And it sits at 20 degrees Celsius. And then the temperature rises to 55.0 degrees Celsius. Once the new pressure is.
So what do we know about gas laws and temperature? What do we always have to do for temperature with gas laws?
Change it to Kelvin.
Change it to Kelvin, because you can never have that 0 in the denominator. And Celsius can have a 0 temperature, as we've all discovered this week. So, how are we going to change 20 and 55 to Kelvin?
273 is Kelvin, so
You just add 273.15.
Okay. 273.15 plus 20 is 293.15.
And you can only keep to the
Oh.
tenths place when you add because of that, so.
Okay.
And Kelvin doesn't get a degree
Okay.
sign,
Yeah.
just gets a K. All right, so then if we add 273.15 to that, what do we get?
328. Yeah, it's just something through.
Okay. So then we plug in, and what do we find pressure to be? So plug into your calculator.
What is 0.7?
And that's atmospheres.
Yeah.
So we thought pressure would go up as temperature went up. That indeed did happen, so good. All right, so now grab that Boyle's Law sheet that you have. Let's see if I can grab mine, I think I actually do have it. And we will collect some data. So we talked about how lots of people measure pressure in lots of different ways. Measure it in atmospheres, pascals, pounds per square inch, lots of other things, right? And we could also measure it in something else like books, right? How much pressure does this book apply to me, right? If I can't actually do it, probably. Ooh, how much pressure is the book applying to my head? A certain amount, right?
One book.
Would this book, one book of pressure, would this book apply the same amount of pressure, right? So I could say this is 2 books of pressure, right? So today we're going to measure pressure in books, particularly Bibles, since they are all the same and handy. I don't have to bring 6 books from home. And they're about the right weight to not destroy my syringe. Because if you get too big of books, it's bad. So first thing we want to do here is, does anyone have a little ruler? I can use a big ruler if need be, but do we have a little ruler handy?
1 week I don't bring my ruler
Yes.
also.
Jen, do you have that art ruler in your bag?
I like never use rulers anymore.
Knew my bag felt light today.
My physics rulers are starting to get warped. This is, I think, the only straight one left. All right. So we want to measure in millimeters here. And who's good with a ruler? Anyone particularly?
No, I'm just kidding.
You would be very surprised at how challenging it is to measure properly
I don't
with a
have
ruler.
my ruler. I
Okay.
don't know where it is. I should
So-
probably find it.
I'll try and do it.
Come on up,
Not
Lily.
just so.
I bet you are. Josh was always amazingly accurate with a ruler. And it drove him nuts when everyone else was like, "What's about?" And he's like, "Oh, 4 significant figures with the ruler, people." So,
Was that in physics or when
Yes. both, but he was nice about it as a lab assistant, his own lab partners. He was like, "How old are we?" So I'm going to line it up. I really wish I could get that little piece down in there, but ooh, that's better. Better. Come on. Stick together. Let the bubble out. Come on. Okay. Ugh, I need the bubble to come out because you need that thing in the neck. Okay, well, that's going to have to do. So we're going to start here, and we're actually going to tape it down, I think. So I want you to line it up so that the sadly crooked little line is right on the
line of the liquid?
yeah, and start it on the 10 millimeter mark there. Then we'll just subtract that, and I'm going to keep it down so that it doesn't move around. And then to the end of the tape, or the, like, we're gonna measure the column of gas, and of course it's gonna shrink as we apply pressure. And actually, let's tape it down here. Let's prop this here. We need room for the books. All right, so we'll line it up and tape it down here so the books can sit. And actually, let's move it away from the edge a little bit too. All right. So, while we're shooting the video, I'm going to kind of show them this, and then we're going to take data points, which will be super boring without them. So we'll just film one, and then, is it ready? Mm-hmm. Okay. Then we're going to tape our ruler down. So we've got this little column of gas lined up on the 1 centimeter or 10 millimeter mark. And then Lily's going to measure, the length of the column to the edge of the tape. So if you just keep measuring to the same place every time, that is probably going to be good. Is it straight? Oops. Yes. Okay, is it lined up again? Because I just moved the ruler. You have to take the ruler too, because I'm excellent at bumping the ruler. Okay. So now we're all set. All right, so what is the length of the little column of gas?
I think it's to the second line, so that's
So like
82.
So 82 minus 10, so probably like 72 millimeters. All right, so we're going with 82 millimeters minus 10 millimeters is 72 millimeters. So when you look at your Boyle's Law chart here on your worksheet, 0 books. The thing has no books on it. It's just sitting there, right? So, you'll have to stay and help Lily. You can record data kind of over there or something. So we're going to put volume in millimeters. That gas column is going to be 73 millimeters. Okay.
0.0? Or just 73?
We can go actually with 0.0 because we can get essentially at least three significant figures from this ruler. So 72. Sorry, the old data is 73. I need to 72. And it's 82 minus 10.
Do we have a laboratory on this?
No, just fill out the worksheet. No more than just fill out the worksheet.
I've got a lab for 6.1.
Oh, great. I will. Anything. Oh, great. We don't need to take it up. We just need to. Okay, so this is going to be, for us, 72. Is this your good pen, Jen? Sorry. I shouldn't be allowed to touch the good pen because I just squish it. So we're going to do one more and then turn off the video. So what is the length of the column of gas when 1 book of pressure is applied? And of course, we have some error because some of the book has to sit on the desk. So Lily will get 1 book of pressure, and then we'll just give you guys the rest of the data as we apply more and more books up to 6.